For the new ones, the Meetup is a monthly event we have. We've been doing it for 6 years now. It's meant to be an open space for the data community to learn and share experience involving AI, machine learning, and data science mostly. For those who don't know me, I'm Matheus Facuri. I'm an economist and data science here at Nubank, and I'll be the host of the event today. So today we have a very special meetup. Is a topic that is very dear to my heart. We're going to talk about causal inference today. Next, we have Sean. Sean is probably one of the biggest voices today talking about causal inference applied to the industry. He serves as data science manager at Lyft, where he works with forecasting, experimentation, and causal inference. Sean has an impressive CV. Like he holds a PhD from NYU. He's worked with the core data science team at Facebook. And if you use Prophet, you probably have him to thank too. Sean is a very amazing communicator. He has other talks on causal inference and other topics. He has, on most of his talks, like they're filled with bits of wisdom, explaining very clear and non-technical way. You should definitely check that out. And because of that, I can't wait to hear what he has to share with us today. Sean is going to talk about us how causal inference relates to experimentation.
Thanks for the intro, and thanks for the invitation to speak. And I'm just thrilled to see, I mean, it's an unbelievable number of people in the audience. So causal inference must be really big in Brazil. I had really underrated that. So it's nice to meet everybody, and thank you for having me. Greetings from sunny Oakland, California. This is a very personal talk for me because I think I had wanted to speak a little bit about why these two topics are things that I learned in separate places, and I've sort of merged them together in my brain, and they've become sort of the same thing for me. But other people learn them separately and might not even learn about the other one. So you might learn about experimentation and not ever learn about causal inference or vice versa. And there's a lot of interesting things to be borrowed from both perspectives. And I think that, you know, bringing these two communities closer together is part of the goal of the talk. So I hope that if you're on the causal inference side and interested in that I get you more interested in experimentation. And if you're interested in experimentation and you run A/B tests, that I get you more interested in causal inference. So that's kind of my goal today. And so I'll talk very quickly about a lot of different topics. So I hope that, you know, if you have questions of clarification, we can hold them to the end, but I'll do my best to explain all the concepts along the way. But I'm really grateful to Nick for explaining a lot of this stuff in advance, so I don't have to go into it. So here's the agenda for this talk. I have 4 acts, and they roughly correspond to periods of my career where I focused on different things. And so I had this like intellectual journey of learning about all these different topics in different ways. And each of the acts has a DAG associated with it. So in Act 1, I worked on observational causal inference, where I had confounding and I had to kind of learn how to deal with things in the way that Nick described, where I had no control and I had no ability to experiment. And then in Act 2, I learned how to use experiments to help solve those identification problems and learn experimentation as a tool. And then Act 3 is running many experiments and experiments at scale in my job at Facebook. And then Act 4, 3 years ago, I moved to work at Lyft, and Lyft has a very challenging set of causal inference problems that aren't always solvable through experiments. So I'll talk about how I had to come back to the causal inference tools that I learned a long time ago and some of the more modern techniques in order to solve some of the challenges that we have at Lyft. So Act 1 is NYU. This is me showing up as a grad student in 2008, and I didn't really know anything. And so I was steeped in this culture of causality is the only way to kind of contribute to scientific knowledge. And here's how we do it. We propose a hypothesis, and it's usually a causal question of some kind, like does X cause Y? And then we go out and try to find some data where we can find like XY pairs, and then figure out if that data is suitable for answering that causal question that we have. And then we do some analysis procedure. Usually this is quite complicated, and Nick talked about a lot of different ways in which this could be a challenge. And then you draw some conclusions, and then you go publish your paper, and everybody's happy because you estimated something causal, and so it means something real happened in the world, and you've estimated some causal relationship. So this is what success looks like. So when I showed up, my advisor had just published this paper, which is about the causal effect of having a friend do something before you. So here it's like adopting a product here, and he studied this product called Yahoo Go. Yahoo Go was like a not a very interesting product, but Yahoo gave my advisor and his team the data to work with, which is why they ended up having it. And it was a really massive data set, so this is really exciting. And so the kind of causal graph that we're working with here is this one where we're trying to identify the effect of a friend adopting a product on you adopting the product, but there's this confounder that you have similar interests. And in this paper, what they do is they use propensity score matching, which is a really well-known causal inference technique, to help reduce the bias of the naive estimates that you would have gotten from the correlations. And they conclude at the end of the paper that at least 50% of the adoption, or at most 50% of the adoption, is driven by social influence, which is sort of like an interesting finding. And so I was sort of like, this is the foundational thing that I showed up in grad school and was like asked to kind of do something like this. So what did I do? I took the same data set and I tried to answer a slightly different causal question, which is, do your friends' usage of the product drive your usage of the product? And I spent a really long time on this, like about a year or more. And I even handed it off to my friend Daniel Rock, who continued to work on it. And we had a good correlation. We showed in the plot at the top that having an active friend on the platform, caused you to, use the product more at every different day after you had adopted it. And then I spent a long time trying to apply this like fancy network panel data estimator. I got really excited about a methodology and burned a lot of time on that methodology. And then at the end, actually the paper is about how that method doesn't really work and that you shouldn't really do that. And I think that was a big learning opportunity for me, is just trying to use the same data and apply different methods really wasn't the right way to think about doing causal inferences. You have to be creative in where the data comes from more than you have to be creative about the methodology a lot of the time. So I started to realize that observational data has a lot of limitations that pose challenges for what we can even really learn about the world. So we have selection bias on the X's that we study, the causes of interest, because we really only study causes where we have a credible identification strategy of some kind. So when you see research where they like found some interesting way to show that something's causal, is like, what other questions did they consider answering that they weren't able to find the data for, is kind of worth thinking about sometimes. And then there's this like selected Y variable, like did the effect that they measured, really, was it in the terms that you would really care about? Sometimes the variables that they collect really aren't the ones that we really care about. And then there's this like retrospective version of this, that we're studying something that happened in the past. Often these papers come out many years later. And so like, are those effects really like, continuing to be valid outside of the context in which they were estimated? So there's like a generalizability issue. And then there's all these validation challenges, like, I think Nick touched on this, is how do we even know if the effect that we estimated is reliable, and would it generalize? And then all the complexity of the analysis that we have to do in order to even make progress on this kind of thing. And on that complexity note, I mean, there's a wide variety of tools, and it can be very, this is a really deep field, and Nick gave you some pointers, but there, you can learn about DAGs and encoding your assumptions about the data generating process. There's a whole, you can spend a lot of time thinking about identification strategies. How can I use that DAG to actually, prescribe some kind of analysis procedure that will work? Can I construct an estimator? Can I use machine learning and other features in order to do a better job of estimating what I want? And then at the end, there's like sensitivity analysis or robustness checks. And each one of these 4 things is a very deep set of things to spend time on. And I think what's interesting is that they don't even really focus on all this other stuff that I tend to care about a lot in practice, is like, where did the data even come from? And what will we do after we estimate something? And how do we know if it was a good job at estimating those things? Are sort of like questions that I think are really a big part of my day-to-day that are not really well covered by the causal inference side of things. And so these were all limitations, and I spent a lot of time learning about all these things. And then at the end of the day, still needed even more, to make progress on these problems. So in Act 2, I was still at NYU, but the thing is that we started to get the idea that propensity scores really weren't going to solve all of our problems, and that we were going to need to do something else. And so this is, I just redrew the same diagram from before with a different flow flow of, here. And so it starts with the same hypothesis. It does X cause Y. But now instead of going and finding data, it says make data. I'm going to go and like design a experiment and partner with a company to run it because, I was in academia at the time. So I can't run my own experiments. I got to go get somebody else to help me run them. And then the nice thing about experiments is they're relatively straightforward to estimate. You can use linear models, and you don't need to think about identification at all. You don't need a DAG. I mean, it's really simple to analyze an experiment. And then the beautiful part is at the end, you get to just report these unbiased treatment effects and not really worry too much about any sources of bias. I mean, you have a variance problem, but you don't have a bias problem. So here's an example of a paper that I worked on that was an experiment. Really proud of this one. We ran this experiment on the social media website that let us collaborate with them, where people could write comments and we would randomize the initial scores of the comments. And the confounding problem we were trying to solve was that if a comment has a higher score, when you see it, it could already be a high quality comment. So the fact that you upvoted it or gave it a good rating, just because it had a high rating, could just be an indication that it was already a quality comment. And so what we do by running a field experiment here is we're randomizing, what scores the comments get when they're born, is that we break the backdoor path in the graph between quality and current rating. And so we're able to kind of get the pure effect of the current rating on people's future rating behavior. And so this was a really fun project to work on, and it really got me excited about experiments, and it made me think a lot about not needing to worry about confounding anymore. It was a really beautiful thing. I think I did have a little bit of misgivings at the end of that experiment, because we spent a lot of time on that experiment and the paper took a really long time to write. And at the end of the day, we estimated, this plot shows that we estimated 4 treatment effects. There were 2 treatments, up treated and down treated. So ones that got +1 and ones that got -1. And we had 2 main outcomes, whether the user upvoted or downvoted. So we had an effect on up treated on up and down vote, and an effect of down treated on up and down vote. So we got 4 parameter estimates from years plus of work. And so I started to think a lot about whether doing experimentation was a good way to build and interact with the scientific community. Given that the estimates, these 4 numbers aren't even really generalizable to other contexts, and that what we estimated was actually pretty in line with theory to begin with. And it also had no clear policy implications for the website that we collaborated with. There was nothing that they could really use this information to improve the website. It was just like a scientific finding. So I started to wonder, like, is just one experiment really ever going to be enough? I think actually we need to think about running a lot of experiments. And it goes back to just like cost of experimentation, is that there's setup time, partnering with the company takes time, getting buy-in, implementing the experiments. And then even if you run an experiment and you do all the setup costs, you still have a sample size concern where you have a variance problem. And so if you always want to run bigger and larger experiments if you can. So the solution to these 2 bottlenecks is obviously to go and get a job and do experiments at a much faster pace. And that's Act 3, which is Facebook. And so these little DAGs on the left are just examples of the DAG of an experiment is just X causes Y, and there's no confounders, and you don't need to worry about any other edges, because those are the only ones that matter. But we get to run a lot of them. That's what the 3 dots are denoting. So at a place like Facebook, now this is the scientific process at Facebook, and it's not very scientific anymore because there's really no science being done. We do run an experiment the same way we did before. But then the goal of that experiment isn't actually to estimate an effect per se, but it's to decide whether the change that we wanted to make was beneficial or not. So it results in sort of like a 1-bit decision at the end of the experiment. And the analysis procedure is like trivial. We just run a t-test, and it's like something that you can do in 1 line of code. So it's like you don't need any of the causal inference, fancy models, synthetic control, whatever. Like you don't need any of that, which is really elegant. And so it really streamlines everything that happens after the new feature idea is almost completely automatable. And so it makes it very fast feedback loop to try new things. The harder part about experiments at Facebook is like, what are the new features and how do you come up with them? And so there's sort of like a missing piece here that doesn't really get filled in. And it's one of the weaknesses of experimentation in a lot of ways, is that there's a little bit of like an atheoretic attitude about experiments where, where are you going to change and where does that come from? there are theories involved here, but they're not formalized the same way that they are in science. So we sort of lack a cohesive view of what the gaps are, what customers really want. It's coming from intuition, but we don't really have a way to close the loop and make experiments tell us what to do next. They just tell us what we need to do now. And so this is a big gap, and sort of like worth reflecting on. Even if you're on tons and tons of experiments, are you really learning something, or are you just doing things that are kind of making small improvements over time? So one framework I have in my head as I started to work at a place where experiments are very cheap, and we have a platform internally at Facebook to run experiments at massive scale, is like the cost of estimating a causal effect. So you could think about like the academic work that Nick presented, which is really solid work, and it's really exciting to see people estimating effects of things like that are really important. But I would call that like artisanal causal inference. It's very it requires like an artisan, somebody who studies the problem really deeply and understands the data really deeply, and can actually draw the DAG and all the domain knowledge that's needed to do that. And then as you move to the right here, you get to a place where you can run experiments really rapidly at a rapid pace. The question is like, what happens in a world where estimating causal effects is really easy and cheap rather than expensive and time consuming? And that's sort of like an interesting lesson to propagate from experimentation, because I think all causal inference at the end of the day is trying to inform something about policy decisions. It's trying to tell us what we could do differently, to make the world more, make the world better in some way. What can you do when experimentation is driven to its natural limit of being extremely cheap? So at the limit, experimentation becomes optimization. It becomes a policy optimization task where we don't care about the experimental estimates anymore. We just want to learn as quickly as possible what tends to make the world a better place. And the intermediate step where we report estimates and try to understand what the meaning of the experiment was is just a nuisance step where we're really just trying to get to the point where we get to the launch decision and get to the next experiment. And so that feedback loop can get tighter. The interesting thing that comes out of that is that, like, usually in science, human knowledge and domain knowledge is used in setting up the scientific studies. So how do we design the experiment? How do we, encode the assumptions as a DAG? How do we do the analysis? And in this world, we don't need that anymore. Human knowledge is used in a different way. It is used in defining objectives and coming up with ideas for new things to try. So humans still have a role in this world, but it's very different than the one before, where like humans were kind of guiding the analysis and trying to come up with the best possible estimation procedure and figuring out where the bias would come from. In an experimental world, we don't really need that. We just need the humans to tell us like what does good really mean and how do we deal with trade-offs, and also tell us what it is that we can do and what have we built and what are we going to be able to facilitate with our platform. So one way to think about all the when causal inference and estimating effects is really cheap is that we can just fill in a big table like this. I call it the experimenter's 3 tensor, which is, it has 3 dimensions, which are treatment space, which are like different treatments that you might try. Context space, which is like what you might know about a person that gets treated. So like demographic data all the way down to like individual level information. And then we have the outcome dimension, which is like, what we're going to measure as outcomes from those treatments. And there could be many different variables included there. And it's all in service of estimating this conditional expectation function, which are kind of the entries in the cell. And so the A/B test that, that most people run in practice is really just a very special case of this more general 3 tensor where we're trying to fill in values and then use this 3 tensor to make a policy decision. So when we do multi-arm bandits, it's because we have a lot of treatments and we're trying to allocate sample size across different columns of this tensor. And when we do like heterogeneous treatment effect modeling, which is a really strong application of machine learning to causal inference, then what we're doing is trying to fill in the columns of the matrix for two particular treatments and then difference them and figure out like which units have the largest treatment effect. And so all the different kind of techniques that are out there for machine learning applied to experiments are often sort of ways of making this matrix easy for us to fill in different values for, and then use it to make better policy decisions. So how do we use a tensor like this in practice? Now that experimentation is really cheap, if we can fill in every cell in this matrix, and each pair of cells in this matrix is a causal effect. we can use it to do optimization. And so that conditional expectation function is just a function where some of the inputs to the function are things that we get to choose, the action space, and then we can apply like an argmax operator on top of that conditional expectation function and get like, what is it that the model implies that is the best thing to do given the situation is situation X. So we have goal Y, we're given situation X, we get to choose A, and then that conditional expectation function directly implies what is the best thing to do given the information that you have available. And so this is roughly where we ended up at Facebook, and sort of like in a place where you can do experiments really cheaply. So here's an example of what that plays out like in practice. Is I worked on this project a long time ago where in Facebook we have these, in Messenger you have sticker packs and you can send people stickers, which are like these little graphics that, have fun little reactions for your friends. And at the very bottom here, we could choose what would be the default pack that would show up for a new user. And that was something we thought maybe new users would respond more to certain kinds of packs than others. So a high bandwidth experimentation strategy that we could employ was to run like every sticker pack that we had available in an experiment and estimate an effect per sticker pack. So this is like many, many columns of that tensor being filled out. So now we have an estimate for like many, many packs, and we can learn like really quickly which ones tend to work well at getting people to retain and use the product a little bit more. And then having estimated that and knowing something about the people, like their countries and ages and demographics, we can engage in policy optimization. So we can choose using Thompson sampling or using contextual-based Thompson sampling, where we're able to kind of choose the pack that we think is best for the particular person at that particular, in that particular place and time, to come up with a better policy and personalize the treatment. And so this is kind of like a good example of what you can do when experiments are very cheap and you don't have to worry about causal inference anymore. Is that like you can get to higher order things because it's very easy to figure out the estimation that you've done implies some sort of optimization as soon as you know what your objective is. The problem with optimization is that often there's more than one thing that we care about. And so the other thing that pops out of the experimentalist view of the world that doesn't come up in causal inference very often is that there are often really strong trade-offs between different courses of action. And so it was really common at Facebook to kind of do these trade-off plots where each one of these dots here would represent a different policy. So policy is a mapping from user to treatment that we have learned, potentially using like a heterogeneous treatment effect model. And then each one of these dots represents like what we think would happen if we ran that policy in production, given the experimental data. This is a technique called off-policy evaluation. In off-policy evaluation, we get to like estimate what would happen in a world where we ran some specific kind of policy. And each one of these dots like kind of like gives you like a bound on like where we'd end up. So there's a Pareto frontier, which is telling you like, if we optimize for metric 1, then we're going to trade off metric 2. And so coming up with how to choose where you want to operate on this Pareto frontier is a really important thing that happens in a world where experiments are really cheap. So the lessons from a world with cheap and ubiquitous experiments is that optimization is the natural end state when experimentation is cheap. So it doesn't even look like causal inference anymore because we've made a causal inference and causal inference engine that we don't even really need. We can completely automate it and we don't need to think about it anymore. So it basically becomes a explore exploit problem. And the effect estimates themselves, the things that we used to spend so much time trying to get unbiased estimates of so we could report it to people, are just nuisance parameters. We don't really even look at them because what we want to learn is a policy which tells us what to do. We don't really care about the effects anymore. So it's kind of interesting, like once effects become cheap, we don't care about them anymore. But I think the optimistic thing is that there's still a real important role for human domain knowledge here in helping articulate the trade-offs and guide the policies in a way that actually aligns with organizational goals. And also developing and building, like, what are the treatments that are available for you to even try? All right, so Act 4 is I switched to working at Lyft 3 years ago because I wanted a new challenge, and I got that in spades. Lyft is a very challenging business and far more challenging than Facebook in a number of ways. But I want to just like quickly just go through like, what is Lyft the product? You know, and I know everybody's in Brazil. We don't operate there. You probably have Uber there, so it's pretty similar. But what is the product that we're building? You could think of it as the app, but actually we have a lot of algorithms that are powering how the app behaves and what kinds of experiences that you're getting. So behind the scenes, we have like, you know, you open up the app, you'll see prices, wait times, what modes are available, you know, what cars are nearby. These are all results of decisions that we have made in the past about how to operate the product. So let me walk you through like what Lyft the marketplace really is. This is a space-time diagram. So time is on the x-axis and space is on the time is on the x-axis, space is on the y-axis. And so here's a driver and they're just like sitting in the same spot over time and not moving. So sessions are when people are potentially going to request a ride. So they open up the app and they check prices. And so we have these two people and they're like kind of, each one is like equally distant from the driver and they're checking the app. And at that moment, we're going to compute the ETA. So first part of our policy is, can we estimate the ETA, or how long it's going to take the driver to get to session 1 or to session 2? Then those sessions receive prices and ETAs. And so the person then decides whether to make a request. So we have a price per session that we're going to charge. And so we have this pricing model, and the pricing model determines like what price we charge. So each session gets a unique price and they get the ETA that we had estimated. And so we're going to report that information to the user and they're going to decide whether to make a request or not. Whoops. And then finally, we have a scoring mechanism which tries to allocate drivers to requests. And so scores are basically telling the driver, hey, go pick up this person versus going and picking up this person. So we score driver request pairs and try to figure out like which one would be the best driver to send to that particular person. So these three functions like are Lyft, the marketplace, and our continual goal as a company is just to make these three functions like just do a better job of running the marketplace. And so that's the job, is like continually to work on these things. And if you think about it, in a lot of ways, what these things are trying to do is estimate counterfactuals of interest. Like if we charged a higher price, what would happen? Would the person accept the ride or not? Or if we scored this thing differently, like would the rider wait long enough for the pickup? And so this is a big part of what we do. So with that in mind, now there's a new scientific process for Lyft, which is different because it actually has causal inference in two phases. And causal inference in the first phase is just trying to figure out which of those functions that govern how the marketplace operates may be failing to do it in a good way. So we're doing some exploratory analysis to find estimates that we're making either about people's price sensitivity or their ETA sensitivity, or about driver behavior or rider behavior that has assumptions that are causing us to make mistakes. And so we're looking for cases where those models are making causal statements about the world, but they're not true. Then we're going to go fix those models. So we spend some time figuring out, how can we build a better model? Is there some identifying variation or randomization that we can use to help us estimate a better causal effect? Then we're going to estimate that model. And then the funny part is that we're going to use causal inference again, because we're going to run that model in production and test it for 2 weeks and see if at the end of the test that Lyft, the marketplace, has improved when we run that algorithm in production. So there's 2 steps of causal inference. One is that we're doing causal inference to make a potential improvement. Then we're doing another stage of causal inference to validate whether that improvement really was true or not. And this is kind of an important thing to think about, is that the A/B test is the ground truth at a company. So this last node here is what we're trying to optimize for. Is we want a shippable change. We want to make a change that actually generates an improvement to the user experience. So the fact that we're using causal inference to be tested by causal inference is important. Is that the only thing that could reliably make a change that would help us detect that change when we apply causal inference is causal inference, because anything else that we would do upstream here to try to fix the models that wasn't trying to optimize for a causal effect improvement would probably not reliably test well. And so that's been my experience at Lyft, is when you use causal inference upstream, then you test it later, it does tend to produce results that are consistent. The reason why we have to run a test at scale is because the marketplace has lots of interference and spillovers. And so it's very difficult to know, just because you made that things work better in isolation, it has to work better in combination with all the other components as well. And then if we make the improvement, then we ship it to the production systems, and all of our data that we analyze comes from production systems. And so our data generating process that we analyze at Lyft is just like a stream of events that were generated by our systems that are running in production. So I know that all sounded really abstract and probably hard to follow because it's complicated, and it took me a couple of years at Lyft to understand really how to make a difference. So I'm going to walk you through a couple examples that I hope illustrate, like, you know, what happens at Lyft and how we make improvements and how causal inference is really at the heart of it. So the matching process, or that scoring process that I described to you, really what we're trying to do is allocate and match available drivers to requests. So requests are, you know, a rider who's asked for a ride, and drivers are sitting around waiting to be matched. And so the extent to which we can perform this matching process efficiently is just sort of like free efficiency for us. If we do it poorly, then we lose rides because riders are waiting too long and drivers are driving too long. If we do it efficiently, then everybody gets a kind of expedient pickup. And so this is our core algorithm that we have to run in production. So what does the matching process really look like is that there's this matrix of all requests on the rows and all drivers on the columns. And then each one of these scores here is an estimate of the expected value of dispatching that driver to that particular request. So we're trying to estimate, like, if we dispatch driver D to request R, what is the probability that the ride completes? And then if those probabilities are estimated without bias, we solve this integer program and we produce an assignment, which is like, this is what we're going to go and actually send to the production system, which will send the drivers in the right place and tell the riders how long they're going to have to actually wait. Then we will maximize rides. And so an important thing that we do is to estimate the entries of this matrix, which is something that we have to do in real time at scale, you know, without any hiccups at all times. So here's the causal diagram that you might think about when that's happening, is that what we care about is the estimate of the effect of an ETA on whether a rider waits long enough for a pickup. And there's confounding here in that the available drivers that we have are affected by market conditions, and market conditions also affect rider patience. And so we have confounding here in our data, which leads to a really interesting kind of correlation between ETAs and rider patience. When ETAs are long, it's because the market is really thin and there aren't a lot of drivers around, and riders actually tend to be more patient in those situations. So when we see, people, ETAs go up and successful pickups don't go up that much, don't go down that much, it's because that there's this confounder in the data. So here's what that looks like in practice. Is you can think about a marketplace for us as having like a dense market and a sparse market. So, and the pink dots are drivers and the purple dots are requests. In a dense market, the drivers tend to be very close to the requests, and also riders usually are pretty impatient in a dense market because they know that there's lots of drivers available. So we dispatch very close drivers in cases where we have impatient riders. And then in a thin market where people tend to be far from their drivers, then we get sort of assignments that have shorter ETAs, and also riders tend to be more patient. So here, this is an important thing to think about, and it's why machine learning and causal inference end up with different answers to the same question. When we train a model, which is trying to estimate this curve here of the ETA effect on whether people are patient enough to wait, we train on the pink distribution, which are the drivers that we actually dispatched to a particular rider. But when we're scoring that matrix, we have to fill in every entry in that matrix, we're scoring the purple distribution. And so there's a selection bias in the data that our machine learning systems have available to estimate this curve on the right. And so because of that, we end up with mixing these two distributions in the incorrect proportions. And it's basically a Simpson's paradox type problem. And we end up with this situation. So this is the same simulation where I applied machine learning to the selected data, which is the pink data, and to the actual data, which is the purple data. And we end up with like that one, the true curve is purple and the confounded curve is pink. And so we end up with this bias in this system if we just train it on the data without considering the causal impact. It's basically the effect of our prior decisions have caused us to have training data, which is biased. So there's a solution to this, which is to use noise in the data intelligently to come up with an identification mechanism. And so really what we're doing is leveraging, here's an example of a dispatch cycle that we would solve where driver one is dispatched to rider one and they experience an ETA of 2.6 minutes because driver two gets dispatched to request two. But if we had moved request 2 up and to the right, just a small amount, then rider 1 would have driver 2 dispatched to them instead. So they get a driver from further away, and they experience an extra 0.9 minutes of wait time. And it's just due to the randomness and whether we're in request 2, which is something they have nothing to do with. So there are lots of reasons why the amount of time that you wait can be plausibly random within some limits. And so there's, if that request 2 was in this pink region, then you'd get one driver. And if it was in the white region, then you'd get the other driver. And this is an example of a regression discontinuity design that occurs in our data in real time as the data is streaming through. So this is a natural experiment that happens in marketplaces like Lyft's that gives us identifying variation in the effect of ETA on rides. And so we care about identifying the slope of this curve here, which is how sensitive riders will be to changes in ETA. And what we look for are assignment changes that generate ETA changes, and the assignment changes happen due to requests being on the decision boundary between getting one of 2 drivers, which is something that we know about from our log data. So it's like propensity score matching. We're trying to find 2 drivers that you could have gotten, equally likely to get them, and you end up with one instead of the other, and it caused your ETA to be longer or shorter. And so we get a little natural experiment out of our data. And just to show you that matters, in practice, we actually applied this technique, and it's all the same causal inference techniques that Nick talked about can be applied to production data. And here the selection bias is coming from our systems, not from confounding about human behavior, but we still end up with bias in the same way. And so the naive estimate would be this orange curve. And then the estimator that we used, where we were able to match and find ETAs with these little natural experiments built in, and we ended up with a differently shaped curve. So this is sort of in testing at Lyft now, and performing well. And it's a great example of how machine learning naively applied to systems that are trying to perform optimization tend to have lots of selection biases baked into them. I have one more quick example, and I really won't spend a ton of time on it, but I just want to mention that one of the hardest problems at Lyft is knowing how much value there is to one additional driver, just being placed on the map at a particular time and place. So if we knew that information, which is a counterfactual question, then we'd be able to do lots of things that are really hard for us to do. And we know roughly that adding more drivers, say we had 9 requests and we kept placing more drivers on the map, that we would get more rides, but there's diminishing marginal returns. But the question is what's the shape of this curve and how does it vary with context? And one of the neat things that we can do is, I'm gonna skip this graph here and just move to here, is that we have lots of experiments that are already running that are determining what the price that we charge for a ride. And so there are lots of cases where we raise prices randomly because we wanna estimate inelasticity, and it causes a ride to complete or not. And then that means that a driver will either show up here or they could show up here. So there's different counterfactuals for the drivers that we can keep track of. And we have instrumental variables that affect whether drivers end up in certain places or not. And so it's possible to use this as an instrument to determine what the effect of that driver showing up in certain places and times is. And so just by virtue of running other experiments, we get this propagation of causality downstream in our systems, which is providing identifying variation for other kinds of causal problems that we have, which is a really neat thing about having all the data and knowing the assignment mechanisms for everything upstream. But you need DAGs to do this. And so it's kind of an interesting case where we're using experimental data, but we're still doing kind of observational causal inference because the experiment was not designed with this particular estimation task in mind. So this is what that DAG looks like. Is we have an intervention node, which is a pure parent node, where we change the price, and it's affecting whether the earlier ride was dropped off, which affects how many drivers are nearby, which affects whether there's a successful pickup for a different ride. So DAGs and causal inference are just absolutely part of what we have to do at Lyft, because we can never make the experiment that we need because they're impossible to implement. We can't intervene on this node on its own. It's just impossible. So the lessons from Lyft are pretty clear, which is that you need to estimate a lot of different counterfactuals to power a marketplace, and you need structural models to do that. And so this leads you more to the Perl style causal inference, where you're writing down DAGs and structural models and trying to fit the parameters of them in a way that aligns with your data generating process. But these always-on experiments that we're running and the knowledge of the assignment mechanisms that we have within the production data provide us the information that we need to do observational causal inference in these settings. And so experiments are actually like letting us do causal inference in a way where we don't need to make as many assumptions as we would if we didn't know the data generating process, which is kind of exciting. I know I've been talking for a long time, but so I just wanted to quickly wrap up and say, like, experiments are a really powerful tool, and they're the gateway drug to causal inference for most people, because you start with A/B tests and you want to do more with them. And so causal experiments are a thing that, like, I think I'm really passionate about, and that automating them and moving more toward policy optimization is a really exciting thing to do. And it's just like the natural progression of causal inference is getting to the point where how do I use the causal inferences that I've made to make my business or the world a better place? And in these settings, theory is not really what we care about anymore. We're no longer scientists, we're more like causal engineers. We're trying to engineer good outcomes and using causal inference and experimentation to do so. On the flip side, causal inference is useful to experimenters too, because not every experiment that we'd like to do is possible. And so we need to use all the tools that, DAGs, causal model, structural causal models, and identification are all sort of part of the problem that we have to solve when we can't do the experiment that we want. But we get to leverage randomness in upstream systems, and that's a very valuable thing to be able to do. So having good logging of all the experiments that you've already run in the past can be very valuable in the future, because it provides you with these little they're not natural experiments, but to you they might seem like a natural experiment because somebody else did it. But it's one of the kind of neat tools that you can have as a causal inference person working in a place where you have other people running an experiment. All right, that's all I have for you. And I really appreciate all your time. I know that was a long talk, and I appreciate the patience. I hope for good questions.
So yeah, I'm back. So thanks for the talk. Was a very interesting one. I'm holding myself not to make all the questions myself. I'll promise all the ones that I read are not from me, okay? But I'll get to choose the ones that I read. Okay, so the first one is, can you explain a bit more on what you mean by you have to be creative in when the data, you have to be creative in where the data comes from instead of creative in the methodology used?
Yeah, that's a good one. So I think a lot of scientists live in a world where they don't have control over systems or ability to intervene, and causality and interventions are really tightly tied. If you have the ability to intervene, then causality is kind of trivial. So what you're really looking for is like somebody else or some other thing made an intervention for you. And so I think a lot of economics graduate students are familiar with like looking for instruments or looking for data sets that can help them answer questions. And that's a really common technique, is just to go and like try to find data that's suitable for answering your question, because you don't live in a world where you're able to kind of intervene on your own and you don't have experimental control. So they're just very different. It's a different regime, but it's very common in the social sciences to work like that and try to find experiments rather than make experiments.
Great. Another question is related to some problems that I think we can't solve with randomization is, what do you do when the feedback loop takes a long time? So there's an example from retail, but I'm going to jump and give a example that I know better. It's like, for instance, when we're dealing with credit and we want to see if playing with things make people default on credit, it usually takes a long time for us to see the effect, like 1 year, and it takes a lot of time to iterate. So how do you deal with that situation? I think I have some similar problem as Lyft, where you will want to estimate the value of something.
I would have loved to have a couple slides in there, and I kind of cut them for time about long-term effects. When I think that experiments are very good at detecting short-term effects quite quickly, and you don't face any compromises there. And then how the short-term effects like correspond to long-term business value and retention of customers is usually one of the most important questions that comes out next. And I have not seen any way to do it that doesn't require some theory of what short-term things drive long-term retention and value, for your customers. And so typically these look things like surrogate models or long-term value models, where you're basically trying to form some forecast of the future, and then try to see how changes in the short-term behaviors result in changes in long-term behaviors of interest. So there's a wide variety of methods there. There's a really good new paper from Netflix that I saw that was nice. That was like a long-term value estimation procedure. But they're like fundamentally unvalidatable models in a lot of ways, because like unless you're willing to wait that long and run a really long-term experiment, then you have no ability to know if you got the right answer. And so I sort of like don't like to work on those things that you don't know if you can ever get it right.
Cool. I've seen some papers from Susan Athey where you have some data for the past where you have long-term and then you introduce experiment. Maybe that could help too. But again, it's a really tough question to answer. Okay. This is a long question. I'll try to rephrase. It's more related to how do you manage an organization that runs a lot of experiments? So let's say, for instance, that you're doing heterogeneous treatment effect, but one business unit generates an experiment, which is the context for another business unit. So let me think about a crazy example. So maybe your Facebook example. You have a feature, let's call sticker, and another user, another unit try to understand if people that use stickers are better suited for some other new feature. How do you plan, like, how do you optimize globally instead of each business unit optimizing locally, and maybe you have some sort of cross bias and maybe one business pollutes the analysis for the other business? Yeah,
it's a really tough one. I think at Facebook, the normal playbook is to assume like everything is additive. So if you have a causal effect that's positive and another team has a causal effect that's positive, then like there will be no. And we ran them. The real experiment that you want to run is the full factorial design, where every unit is changing experiments in a way that you can actually interact with every other unit and then see if there's like negative interactions. And we have tested for that at Facebook. That was like a project that I had somebody work on for a little while, which was like, do our experiments from different units, interacting in ways that are causing bad effects? And there's stories about that from places like Google, where one unit will change something about search and another unit will change something about search, and then like it will result in some disastrous user experience. In general, like it's something that people don't, it's understudied, and it's kind of like one of these things where people think of it as second order, and I haven't seen any evidence that it is potentially problematic. But at Lyft, it is a big problem that teams don't coordinate, because the product is so focused on one particular goal. Products like Facebook have a wide surface area, so if you improve things like groups or events, then it doesn't really change the experience for newsfeed very much, and that's a plausible assumption. It's actually a really good tool for DAGs, if you think about it, is that if I can draw a DAG and I can see a path from one team's product changes to my team's goals, and that path is plausible, then it might be worth figuring out if there is a causal effect there. And that essentially what you have done is assume that there is no path between those nodes in the DAG by working independently. And so that's a really good case where like thinking formally and having a theory of your business can be a valuable thing to do. I've also seen that teams coordinating on experiments is really important, and so having cross-company launch meetings and discussions about experimental results is a really valuable coordination tool.
Cool, amazing. Thanks for the answer. The next one is, well, about continuous treatment. Thankfully, someone asked about that. So you said that one of your treatment is ETA. How do you deal with the process of handling a continuous treatment like ETA? It's not as trivial as probably randomization, because you have to make some assumptions on the functional form, I guess.
Yeah, it is pretty challenging. And I think like all of our continuous treatment effect models rely on some parametric functional form. And so once you've chosen a parameterized curve, then really it boils down to like, does the curve that you have parameterized produce effect estimates that are like locally consistent with the experimental evidence that you have? But I will admit that we don't really have a good procedure for fitting those models that we're very happy with, or for validating those models that we're happy with. And I think continuous treatments really are particularly challenging problem, and that I haven't seen like a really out of the box easy way to do it. I think we just rely on a lot of plots and visualizations and a lot of like ad hoc validation for those models. Whereas I think that, you know, treatment effect estimates from other sources are quite easy to do. Things like there's like experiment splitting, cross-validation ideas apply quite readily. But for continuous treatments, I think it's a little bit harder to know if those models are doing the right thing.
Yeah, I've struggled with that too. Another one on company organization. Sean, how do you and team spread this methodology and thinking process over the, I guess, entire company? I imagine that there is a culture shift in making a company go from a predictive place to a does X cause Y place. Are there specialists within the company, or do we provide any training? Is there a plan to scale this knowledge?
Yeah, I think that's a fantastic question, because it gets at the heart of that. None of this matters if people don't believe that it matters. And so it's getting a culture of people that think critically about, you know, all your systems and whether they have correct estimates in them and what would be the potential confounders is really important. I think that the two tools that we have are education. So we do have a causal inference course at Lyft that just kicked off today, actually. So there's like 13 weeks of content, and we have over 100 people signed up to attend. So I think tools like that are useful, and just getting people to think about it as a lens through which to look at your business problems and see if it changes the answer to any of the questions that you're asking. But the other tool I think has been examples, and so that example that I gave about the driver dispatch decisions and how the data was confounded was a really great case study to present to the machine learning engineers and show them like two curves, one that was estimated with machine learning, one that was estimated with a causal model, and how they were different and substantively different. And then having that correspond with a successful test later, so that the machine learning engineers could learn, oh, it's not just the AUC of the model on the data that we have, it's actually like a very different thing that we want to evaluate it on. And we want to produce a model that will produce a successful A/B test later. And then showing them an example of that you could do that, and that it wouldn't provide the same answer out of, in the held out data that they're used to was a really important case study. And I think it just takes a lot of case studies like that to kind of get people on board. And it's honestly really exhausting and time consuming sometimes.
Yeah, no, we went to a process like this. It took a very long time for the first convincing, and then things started to flow more smoothly. Okay, so I guess final question is, randomness and exploration can be expensive for business. Do you use any strategy to explore more deliberately, intelligently to maximize what we can learn, or is truly random? And I think a follow-up, which is mine, it's not written, is that if you use some strategies like Thompson sampling or contextual bandits that they alter the assignment mechanism, it's much more complicated because you have to be careful with stationary. Like, as Nick was saying, like maybe you have a Thompson sampler that just posts option A close to Christmas, and then the algorithm will take a long time to learn that it's only due to confounding, that by chance you scale things up when things would already go up naturally. So
yeah, agreed. All those are great questions, and I think stuff that we're still sorting out. I wish there were like books about this, and there just aren't. But the shorter answer is that if we have experiments that we're going to leave on for a long time because they generate valuable data, then we want to be able to estimate the cost of those. So you can do an experiment versus no experiment. So there are tests that you can run where it's, some 50% of the users are in the experiment, 50% of the users are in production, and then you can estimate the cost of running the experiment. I have found some interesting results there, where sometimes running experiments doesn't cost you anything, because you lose a little bit when you go to one side of the policy, and you gain a little bit when you go to the other side of the policy, and it kind of like neutralizes. So I found them to be not as costly as people think that they are in general, because you're not really that sure about being at the optimal state in general. And so the experiment is just exploring around a state that you're not really sure about, then it's just as likely to improve things as it is to make it worse. for the Thompson sampling stuff, I think, there's a concept of like an exposure log in an experiment where it's what treatment did the user get at this time. The general version of that is a propensity, exposure log with a propensity score. And you have to log, it's called counterfactual logging. But if you're logging what you did, you have to log what else you could have done and what the probabilities of those things were at all times. And so it adds logging burden, and it's very important that engineers who build logging for these systems are aware that they need to log not only what they did, but also like what the probability of doing that thing was. And having that data is very valuable, because that's basically what you're looking for when you're trying to debias the kinds of stuff that you're talking about. You're looking to reduce confounding from the bandit having introduced confounding and treatment assignment, and so you just need to know the treatment assignment probabilities in order to do that.
Great, thanks. I said last question, but I actually have one last that I also made to Nick, which I think is a great question. How do you see the future of the area, and what are you excited in causal inference about now? Like, what are you working on? How do you see this area going forward?
Yeah, that's a great question. I think that the things I'm most excited about are, like, honestly, they might sound a little boring, but I think model validation and understanding whether your model's any good is the thing I've seen them struggle with the most at Lyft. Is we produce models, there's model A is the old one and model B is the new one, and it's very difficult to know which one is better, and it's not like a supervised learning problem. So anything that I see about that, I instantly really want to know more about it, and I think that's really important. And then I think, like, automation and quality control of these things is a big thing, which is like, once you can do it, and you can do it more than once, then the next question is, can you keep it in a quality state over time? I think of it almost like a factory producing widgets, and the widgets have to be high quality. So if every estimate is high quality, then your system will run just fine. So it's kind of this equivalent of monitoring and quality control for a supervised learning system, but for causal effects is really kind of like where I'm most interested in these days. And it's just because of the lens of, like, I work at a company where when we make mistakes, we lose money. So and the mistakes are from having models that don't do what we think that they're supposed to do. So that's the lens that I have a lot of the time.
Great. And well, glad we have Nick here. Maybe he can write a book on causal inference on the things we still need to answer. So I think that's it for the talk. Sean, feel free to plug anything you want. Tell us where to find you.
Yeah, I'm on Twitter and LinkedIn, and so happy to chat with folks there. And always feel free to email me or message me with questions, because I love talking about this stuff. As you can tell, it's very fun for me. Well,
Nick and Sean, thanks a lot for your time, for being very, very generous. I know you're pretty busy, and I guess you see that folks here in Brazil are very excited about this stuff, and very glad to have you. Have a great day. And everyone else, bye-bye. Thanks for being here, and have a great night. Thank you.